Okay, we're recording. We're going into chapter 12. All of the assignments are posted, but the completion rate is low. Just let me know if you need an extension on those, um, and I'll extend those for you so that way you can get the full points. Before we dive into chapter 12, which I think is a very interesting chapter because it's very relatable, right? We all have ears we can hear. We all are interested in instruments and things like that. So it's kind of a nice chapter. Before we get into it, though, there is a concept from the last chapter that we didn't get to cover um, because we didn't have enough time. But we can actually cover that topic pretty quickly and then dive into chapter 12. So the topic that I'm talking about in particular is energy transported by waves. So that's section 9 in chapter 11. So a recap here, so to speak. You guys went over it, right, as part of the assignments for last week and probably read it in the chapter. But let's go ahead and just quickly recap it. So 11.9, the section is called Energy Transported in Waves. We'll just call it Energy in Waves here. Okay. The way that energy is carried in waves is not too much different than how energy is carried in these mass spring systems. In fact, in order to kind of derive a formula for energy carried in a wave, we can draw analogy from this kind of situation here. So imagine we have this mass on a spring. We showed many times now in this class that the energy that's stored in the spring, if the mass is stretched a distance a, is 1/2 Ka squared. And that is the total energy stored in that system. So if I let go of that mass and it starts to vibrate or oscillate back and forth, then the total energy will always be equal to 1/2 Ka squared, right? Of course, as that mass comes closer to equilibrium, it gains more kinetic energy and it loses some of this potential energy right here, which is the energy stored in the spring. And so those energies convert between kinetic and potential, but the total amount of energy stays the same. That's simply conservation of energy. Now, one of the things that we like to talk about when we talk about energy is how much energy is being output per second. That's what we call power. Right? Power is the amount of energy output or energy dissipated per unit time. And sometimes maybe we even see this formula as an amount of work done per unit time. That's equivalent. Those two are equivalent right there. So let's go ahead and write some of that. So power is energy per unit time. But as I'm going to show you here, and actually I figured out a nice way, thanks to one of my students in my other class, they pointed something out to me, like if I'm on Windows, I can actually copy figures another way. Let's see if this worked. All right, this worked, so that's nice. Oftentimes when we talk about waves, for example, let's suppose you have like a speaker, right? So we're going into the sound chapter, we're going to deal with situations where we have like loud noises or music or something like that is playing, and you have a speaker which is emanating sound from the speaker, right? So you can think of like a speaker as like a point, and it's a source of sound, and you have these sound waves kind of emanating outward three-dimensionally, kind of in a spherical way. And so here we have kind of that idea. So some sort of source in the middle here, and that source is emanating some kind of wave in all directions. Of course, if you emanate something in all directions, right, and it has, a certain velocity, that's going to emanate outward as a sphere, right? A sphere, all the points on the edge of a sphere are the same distance away from the center. So it's nice to have an expression for power output, but power output doesn't really encapsulate the fact that if let's say I do have a speaker, the speaker has a certain power rating, maybe it's 1 watt or half a watt or something, that if I get further away from that speaker, then the sound that I hear is diminished, right? If I'm really close to, if I put my ear up next to a speaker, it's really loud, right? If I walk a couple meters away from that speaker and I don't change the volume on the speaker, then I hear the sound is diminished, right? It appears like it's at a lower volume for me. And so what we do is we take this notion one step further and we define what's called intensity. And this concept of intensity allows us to kind of understand why, when we get further away from a speaker, the sound appears at a lower volume to us. So it has to do with this idea of intensity. So intensity is power per unit area. And the area that we're talking about here is the area that this wave is distributed on. So if I have a speaker, it's playing some music, right? When that speaker emanates some sound out from it, that sound is emanated in a spherical fashion. So it's emanated in all directions. So if I go behind a speaker, I can hear the sound the same as if I'm in front of the speaker, as if I'm above the speaker or below the speaker, right? So in all directions, the sound is emanated equally. That's not exactly true, because if you really look at the design of a speaker, they tend to be designed in such a way to project sound more in one direction than in other directions. But in principle, it's approximately true. So even when you do project the sound in one direction, you can still approximate those waves as spherical waves. Okay. So this idea of power over area. So more often than not, the area in question here will be a spherical area. So a 4 pi r squared. So where's my mouse at? Right here. So most often, area will be 4 pi r squared. Okay. So that power will be distributed on the surface of a sphere. This is also true for something like the radiation energy that reaches the Earth from the sun. So the sun is emanating all of this radiation in all directions, right? But only a small fraction of that radiation actually reaches the Earth, and just so happens to be enough to keep the Earth kind of warm, right? We'll talk. I'll bring up another example shortly when we get into the chapter 12 stuff about the sun, when we talk about sound power and sound intensity. So most often the area will be a sphere. Now, right away, you can see that we can compare different intensity levels by taking a ratio. So let's say we have one speaker. Let's go ahead and draw like a short picture here. So if we had one source of sound, let's say, doesn't necessarily have to be sound. Let's call this source 1, and we have source. How do I want to do this? Oh yeah, as a matter of fact, we want to use one source. So suppose for a second that we have a source of waves. So let's go ahead and draw like a wave here. Maybe I'll use like red or something. Try and make a circle and put it this. Okay. And this source has a certain power rating. And that power rating, let's say it's just P here. Some number of watts, maybe 1 or 2 watts, let's say. Um, that power is distributed over a spherical surface at a distance r1. Okay, and I investigate the intensity at that radius r1. Okay, and the intensity at that radius r1 I'll call I1, and I1 is going to be the power over 4 pi r1 squared. Now suppose I do the same thing again, but this time I investigate that same speaker, that same source, but at a different distance away, say R2. Okay. And I'm investigating the intensity, so I'll call it I2. And I2 is the power of that source again, but now it's 4 pi R2 squared. It's no longer R1 squared. Look, we're further away now, so we divide by R2, 4 pi R2 squared. Okay, we can compare the two intensities now. So I can take the intensity I1 and divide it by I2, or I can do I2 divided by I1, whichever way you want to do it. Let's take I1, let me write it a little bit bigger. Let's take I1 divided by I2. And we'll go ahead and do all the steps here just to start things off. So 4 pi r1 squared divided by p over 4 pi r2 squared. And notice, because the source is the same, the power output of that source is the same, and we have some factors of 4 pi here, a lot of this stuff is going to cancel for us. And the ratio of the intensity I1 to I2 is equal to R2 squared over R1 squared. Now, I kind of don't like it when I see a formula where I have like 1 over 2 on one side and then I have 2 over 1 on the other side. I personally like it a little bit better if I put all the 1s on one side and all the 2s on the other side. So that way I don't have to remember which one goes on top. So I would rewrite this formula as I1 R1 squared equals I2 R2 squared. And so this is nice because it allows us to compare ratios. So if I know that I can measure the intensity at 5 meters away from the source and measure the intensity, or excuse me, if I am 5 meters away from a source and then I go to 10 meters away from that source, I can take the ratio of those distances squared and I know the ratio of the intensities. So then all I have to do is know one of the intensities and I know the second intensity. Okay, so we know, if we know any of these three quantities, we can figure out the other one, basically, is what I'm saying there. So yeah, that's just a quick overview there of intensities. In general, it's not always going to be 4 pi r squared in the denominator. For example, the next little topic we're going to do before we go into chapter 12 now, we're going to look at a wave, a wave which is traveling outward, which is sometimes called a plane wave. And in that situation, what we can do is I can, again, copy this figure over. Save us some time here. Hopefully it's not too blurry there. We have a wave that's traveling in space, and we're saying that in this small region here, in this small volume, there's some energy carried by that wave. Okay. S here is the surface area of that box, the face of that box, the front of the box there. And then the depth there of the volume is called L. But whatever the velocity of the wave is, times the time that it travels, that's going to sweep out a region there. So that L value, whatever L is right there, is given by the velocity of the wave times some small amount of t. Really, the book should probably put a delta t here and say that delta t is small. That's probably the proper way to do this, but they don't do that here. And we can calculate the amount of energy that's stored in this wave by drawing analogy to our friendly equation 1/2 ka squared. Okay, we just have to remember a couple things. And one of those things in particular that I don't like how they write it in the book. I think it's a little bit simpler to, I'll write what they write, but then I think it's a little bit simpler to write it another way. So if you remember when we looked at the actual representation of waves, the mathematical representation as sines and cosines, they write k as 4 pi squared mf squared. Okay, but there's an easier way to recognize this relationship here. So if you go through the motions of calculating the frequency, which we did do this in class, remember, the angular frequency of the mass spring system, we got the square root of k over m. What are we going to get if we solve this for k? What are we going to get if we solve this for k? Well, we have a square root, right? How do we cancel a square root? We have square both sides. Right, so we have omega squared equals k over m. You can multiply m to the other side, right? So k equals m omega squared. And this is so much easier to remember than this right here, right? This is a nightmare to remember. K equals m omega squared, not so bad. The relationship here is, of course, coming from the definition of omega. Omega is 2 pi times the frequency. And if you remember, frequency is the number of cycles per second, right? So 1,000 hertz is a frequency, 1,000 hertz. That means 1,000 repetitions in 1 second. So something happens 1,000 times in 1 second. 1,000 hertz, that's kind of like a high-pitched, sound as well. Okay, given this information here, we can actually rewrite this expression for the energy, which is better adapted to a traveling wave, so when we have a spring mass system, that mass is oscillating back and forth. It's not moving in space, right? But we can have waves which travel outward in space. Think again like the sun's radiation, or what we were just talking about with speakers and sound. Those are waves that actually travel outward. We say they propagate outward. This formula here, of course, is not applicable to a wave that's traveling outward, because there's no such thing as a spring constant for a wave, right? Spring constant is for a spring constant, or a spring constant is for a spring, I mean. So we can adjust that rather easily by simply replacing k with m omega squared, or by replacing it with the 4 pi squared mf squared, which is much more difficult to kind of remember. But Let's go ahead and replace it first with m omega squared, a squared, like so. And this is not included in the book, this m omega squared piece. They do everything with this right here, so this more complicated expression. But everything is, the analysis is exactly the same if you just replace the m omega squared with 4 pi squared mf squared. Okay. Now the idea here is that, and also the reason. So the idea first. The idea is to calculate power. So here's our outline of what we're doing here. So we want to calculate power and then calculate the intensity. Okay. This A right here is the amplitude, not the area. Okay. So be careful when you're actually reviewing this, right, or looking it up in the book. This A here is the amplitude. Remember, it's how far we stretch the spring. Now it's going to be the coefficient, the number that goes in front of a sine or a cosine, right? From your pre-calculus class, you know, amplitude is like A sine, theta, right? This is the amplitude, the A right here. Maybe, you also have omega t plus, some phase angle, right? Something like this. And then you have the vertical shift as well, right? And then maybe you have I should probably put it maybe a little bit more general. So then maybe there's like a x minus x0. This is the horizontal shift part, right? B here is related to the frequency of the wave, how many times it oscillates per second. And then you have like some phase shift, and then, well, maybe I should call it C, huh? C. And then maybe you have some sort of vertical shift as well, right? So that's kind of like the general pre-calculus sign, right? So that amplitude intuition carries over to here in physics, right? So it's the same thing. We're calling the same thing amplitude here. Waves have an amplitude of oscillation, but they can also travel in space. Whereas a spring mass system, it just oscillates in place. It just vibrates back and forth, and it doesn't move through space. Okay. All right, so let's calculate the power. So power is energy per unit time, right? Power is energy per unit time. And so what we need to do is we need to replace the mass in our equation. Okay. This is kind of another issue. If we have a wave, what is the mass of the wave, right? Well, that doesn't really make any sense because the wave carries energy. It doesn't carry mass with it. Although maybe a more modern physics approach would, we have energy and mass equivalence. That's like Einstein's E equals mc squared equation. But we're not doing that here. So in this case, the waves are not carrying any mass. So we should probably replace mass with density times volume, and replace volume with, what is the volume? Well, the volume here is S times VT. The volume there is S times VT. Let me try and get all of that in the picture here. So the volume in that figure there is S times VT. Give you a second to catch up there. So volume is S times VT. S is area, yeah. S for maybe like surface area, right? S is the area here. Okay, so hopefully that was enough time to copy that down. So I'm going to scroll down now. Now that we have the mass as rho SVT, we can plug that in. 1/2 rho SVT omega squared A squared. Now, if we want to get power, power is just take this thing and divide it by T. If I take this thing and divide by T, I have to scroll out for a second to drag this down. I forgot. Come back in here. There we are. I got to divide this whole thing by T. That gives me power on the left side. On the right side, I get 1/2 rho S V. No more T. I'm dividing by T. We've divided out the T. There's no more T here. We divide E by T, we get power. That's P. And then another simple step. Well, if we want to go from power to intensity, we divide by the area. And the area here is S. So now we'll go ahead and divide by S. And then we get intensity. So 1/2 rho V omega squared A squared. Again, A is the amplitude here. A is the amplitude. And just to complete, the picture here, this indeed is the same formula as what you're going to get in the book. In the book, you're going to get 2 pi squared V F squared A squared. That's what you're going to get in the book. But it is the same formula. Okay. All right, so that is all that I wanted to cover from that little portion of chapter 11 there. So are there any questions about that? Okay, so I have a question for all of you. It's a simple question, nothing we should spend too much time on. Suppose I have a wave, it's traveling in space, and I double the frequency of the wave. How much would the intensity change by? So I'll type it in chat. So double the frequency of the wave, how much does the intensity change by? Double the frequency, what happens to the intensity? Good. So intensity goes up by a factor of 4, right? So that's the thing, is higher frequency waves carry a lot more energy, right? So just this simple formula right here can help you understand, things like X-rays, for example. So X-rays are really high energy waves, electromagnetic waves, in fact. And so they penetrate through the soft tissue in your body because they're really high energy. Okay, but bone is really sturdy, and the waves are the waves are actually scattered off the bone. They don't actually penetrate the bone. Okay, so here's one interesting fact that we're going to carry with us into chapter 12, and then we'll go into chapter 12 here. And that is the amplitude here. What we're going to see is that intensity is related to volume. And when I say volume, you of course have to understand I only mean in the case of sound, right? If we're talking about some other kind of wave, then volume doesn't really make sense anymore, right? So intensity is related to volume for sound. And the volume here depends on amplitude. The amplitude, excuse me. So what I wanted to say was, no, I misspoke here. I said it. I said it completely backwards. I meant to say this. Amplitude is related to volume. Sorry. The way you can see that, you can actually see that on a speaker. If you have a speaker where you actually can see the that little soft rubber part of the speaker kind of moving outward when you hear, like the best example is like if you have a big bass, right? Those really loud bass sounds, you can see that speaker move when it makes that loud bass sound. If you crank up the volume, the amount that speaker moves is more because you increase the volume, and you're going to make the amplitude of those oscillations bigger. Okay, that's what I wanted to say. Now that is related then to the intensity. So the two really are related to one another, but really what I wanted to say is amplitude is related to volume. Okay. But as you can see, the intensity also depends on frequency. Okay. Since the intensity depends on frequency, this means that different frequencies can appear louder, or I guess maybe softer to your ear. Okay, so your ear is the sensitivity, so to speak, or your perception of the loudness of a sound is going to be related to the intensity. Okay, not only the intensity, but also the excuse me, I'm misspeaking again. Sorry, is related to both the frequency and the amplitude of vibration. The intensity is what you're experiencing at your ear. Okay. So let's go ahead and get into chapter 12 now. So the first thing that we need to understand maybe when it comes to sound is how sound actually propagates. Okay, so chapter 12 now. So chapter 12, sound. Okay, sound waves are simply waves carried by the vibration of air molecules. Okay. The medium through which sound waves travel is air itself. Now, what happens when you take the air away if you try to make a loud noise in a vacuum chamber where there's no air? Well, what happens is you don't get any sound. So, for example, when astronauts landed on the moon, they had to communicate via like wireless, communication devices, right? You couldn't just yell out without turning on your walkie-talkie or whatever they were using. You couldn't just call out to your partner who's standing 5 feet away from you and they're going to hear you because the atmosphere on the moon is very, very, very less dense than Earth's atmosphere. There is a bit of an atmosphere on the moon, but it's very, very low density. And so the sound waves wouldn't be able to travel in that medium. So if you call out to your partner on the moon, they're not going to hear you. So you have to use some sort of radio communication, so wireless communications. The second thing I want to emphasize is, of course, in the movies, for example, like Star Wars, you often see like ships firing lasers and stuff, and you have all these sound effects playing, right? And you hear these explosions of like ships blowing up and stuff. Is not very accurate. So if you're on the ship, right, and you have air in the ship, then you would definitely hear an explosion on that ship. If some laser beam or something hits your ship and causes an explosion, if you're in the ship, you're going to hear that. But if you're on the ship who fired the laser beam, you're not going to hear any of that sound because there's no air between you and the ship that where the explosion occurred. Okay, so be careful when you watch movies, and a lot of stuff in movies is not scientifically accurate, right? So don't make any scientific conclusions based on something you see in a movie. Okay. In any case, how the sound waves are carried by the air depends on the temperature of the air. Okay. Now, temperature is not something that we've covered yet. It's actually coming in the next couple chapters. But basically, temperature is related to the speed of the molecules that make up the air. The average speed of all of the molecules which comprise a gas, is going to be directly related to the speed of sound in air. Okay, so that's the next thing I want to write. So speed of sound depends on temperature. Now, we don't have to have a theoretical description of why sound depends on temperature. We could simply perform some experiments and see how sound depends on temperature, right? If I have a cold room and I make a sound on one side of the room, and that sound then is detected on the other side of the room, right? I can measure the speed of sound there by knowing when the sound occurred and the difference in time that it takes to measure that sound on the other side, right? And then I could crank up the thermostat, make the room hotter, right? And perform the same experiment again and see that, oh, okay, so the speed of sound is bigger in a warmer room and it's smaller in a cold room, right? So I could perform experiments to determine that fact. And in doing that, I could make a bunch of measurements and see that the speed is somewhat linear, not exactly linear, but it's somewhat linear and to a very good range of values here. The speed of sound, I'll use v sub s here for that, speed of sound. So, it's written right here. So speed of sound here is v sub s, is 331 meters per second plus this numerical constant here, 0.6 times the temperature. And let's put the units in there. This would be meters per second per meters per second per, and then I believe for the temperature here in the book they use Celsius, I believe. So put degrees Celsius here. You actually have to be very careful. Some of you may have taken chemistry, and oftentimes In physics and in chemistry, you have to be very careful about if you plug in Celsius versus Kelvin, right? If you're dealing with ideal gas law, you better make sure you plug in Kelvin, the absolute temperature, right? Um, but in instances where you have a formula which has a delta T instead of a T, it's okay to plug in Celsius because the difference in degrees Celsius is the same as the difference in Kelvin, right? This particular formula that's presented in the book, which by the way, I haven't finished it off yet, times T, where the units here on T are going to be degrees Celsius. The book has done something kind of nice for us, and they've made sure that this factor out here in front is the correct factor when the temperature here is plugged in as degrees Celsius. Okay, so they've taken care of that for us. So we can just plug in degrees Celsius, excuse me, and we're okay. All right. The formula is usually not linear. It depends on the square root of the temperature. If you have a very large range of temperatures, you better use a formula that has a square root in it, because the linear portion is going to go away very quickly. So if you're dealing with temperature changes on the order of like maybe 100 degrees Celsius, maybe you're okay. But 1,000 or 2,000 degrees Celsius, it's not going to be okay anymore. It's definitely going to differ from linear behavior. Okay, so from this expression, I think you guys can just answer this question for me. At a temperature of 0 degrees Celsius, what is the speed of sound in air? At a temperature of 0 degrees Celsius, what is the speed of sound in air? Just write the answer in chat. Okay, very good. Now, what is the speed of sound at room temperature? So we take room temperature to be 20 degrees Celsius. So room temperature is 20 degrees Celsius. That's just a definition. That's not really, like, most people don't have their thermostat set to 20 degrees Celsius because that's about 68 degrees Fahrenheit. That's, I think most people would consider that pretty cold. But that's what we use as definition for room temperature, 20 degrees Celsius. Okay, good. So yes, good. So 343 meters. Oh, a couple people haven't had a chance to answer yet. So 20 times that 0.6. 20 times that 0.6 gives us a 12, right? Add the 12 to the 331 and you get 343. So that value is, it's pretty useful to have remembered. Like if you can remember the 343 meters per second and the 331 meters per second, that will help you get through problems faster. But of course, on a test, I would just give you that information, unless I'm asking you to calculate that information, in which case I would not give you the answer, right? But yeah, so the next little bit that I think we should just quickly mention here is that the frequency of sound, of a sound wave, is related to the pitch that you hear for that sound wave. Now, frequency and pitch are not, they're definitely a related concept, but they're not exactly the same concept. For example, as we age, our hearing tends to shift downward a little bit in pitch. And so somebody maybe like a senior citizen, 65 or so, might hear sounds a little bit flat compared to a younger person. And so pitch is like your perception of the sound of the notes that you're hearing. So frequency and pitch are not exactly related, but if you go on your entire life interchanging the words pitch and frequency, likely no one will ever notice a difference. They're virtually the same. So that's enough about that. Let's try to get into um, a little bit of an example here because I've been talking for a while. Um, Actually, this would be a nice question. It'd be a nice conceptual question, but I want to get you guys a calculation question here. Let me see if I can. See if I can do this. Oh, I can't. Okay. Let's save some time here. Can you guys read it when it's this large? Or should I type it out by hand?
It's not bad. I think it's
If I make
not.
it, is it better like this or?
Uh, it's okay. It's definitely. Why don't you zoom in on the page? Oh yeah.
That's better.
Nice.
Okay.
Okay, thank you.
Yep, there we go. So auto-focusing with sound waves. So the way your phone or camera actually autofocus is by sending a sound wave which you cannot hear. And then detecting that sound wave as it reflects off of surfaces that are in its field of view. So oftentimes if you have like an autofocus camera, and something like, let's say you're trying to take a picture of your family or your friends or whatever, right? And some object passes in front of the thing you're trying to take a picture of, then it ruins the focus of the camera because there's that detection there um, of that what's called ultrasonic sound wave. It makes contact with the object that came in front of everyone, and then the camera is like, oh, I better refocus. Everybody's moved closer now, but then nobody really moved closer, right? Somebody just passed in front. So there's an interesting application there for sound outside of the audible range. Okay, so I never read the question actually. Let me go ahead and read the question while you guys are copying it down. So autofocusing cameras emit a pulse of very high frequency ultrasonic sound that travels to the object being photographed and include a sensor that detects the returning reflected sound. Excuse me. See figure 12.1. Oh, there is a figure. Oh, okay, I see it. I didn't notice it. So let me go ahead and pull the figure as well. There's the figure. To get an idea of the time sensitivity of the detector, calculate the travel time of the pulse for an object 1 meter away and 20 meters away. By the way, you can assume room temperature here for this problem. I notice it does not tell you what to use for the speed of sound. Whenever you're not told, anytime you're not told what the speed of sound is, it means you should take the speed of sound to be 343 meters per second. Okay. Always take the speed of sound to be 343 meters per second when it's not given to you. I'll give you guys maybe another minute on that one. You can put your answers in chat once you get them. Just grabbing some water there. If the intensity of the sound that the intensity of my voice was decreasing, you know that's because I moved further away from the microphone here. Just put your answers in the chat when you get them. We have one answer in the chat. So we have some disagreement for our answers here on this one. It's always good to see disagreement. You can double check your work and see if you made a mistake or something. I'll give maybe another 30 seconds here for this one because I see a lot of you are still working. Okay, put whatever answer you have in chat. Like if you just have answer A, put answer A in the chat, just so I can see some progress here. If you didn't have a chance to get part B done yet, that's fine. Let's go ahead and take a closer look here at this problem now. So I'm going to zoom out. Let's go over the question now together. So the key here is recognizing excuse me. The key here is recognizing that the ultrasonic sound has to travel to the object and then back to the camera. So if something is 1 meter away, then that means the distance that wave has to travel is 2.0 meters. So the amount of time that that's going to take is 2 meters divided by the 343 meters per second. This is going to give us, what is it, about 5.8 milliseconds, something like that, for part A. Now for part B, it's the same sort of thing, except it's going to be, so this is TA, I guess, and we'll call this one TB. This is 40 meters over 343 meters per second. And this one comes out to 120 milliseconds. Rounding those off to 2 sig figs, right? Okay, any questions about that one?
Is it normal to put it in milliseconds instead of seconds?
It's a choice.
Oh, okay.
Yeah.
Thank you.
if you want to write it in scientific notation or so. Usually you want to just write it in whatever, with whatever units are the easiest to kind of read the number. You don't want to write something that's like 0.00 something something. You want to maybe go, you want the number in front to be between maybe 1 and 1,000, and then use the right metric prefix. So like if you have 0.058, right, seconds, you want the number to be between 1 and 1,000. So I'd want to move this decimal over here, or maybe over here. You want to do that in units of 3 though, because then you can use a metric prefix. So there's going to give me milli, right, if I do that, if I move it over. So that's kind of the general idea. And then that avoids, writing things kind of that look kind of strange, and kind of avoids using powers of 10 when you don't really need powers of 10 because there's a prefix for that. But for something like maybe you've seen in chemistry, like Avogadro's number, right? 6.022 times 10 to the 23rd. I mean, in this case, you can't really, there's no prefix for 10 to the 23rd, right? So you just kind of are forced to use scientific notation. So that's the idea there on that. Yeah. All right. So let's now move to, and I guess I can zoom in on the figure again, and it looks kind of decent. This is what an actual sound wave looks like if you image the molecules in the air when you hit a drum, okay? So we can clearly see there's these clusterings of air molecules. And when the air molecules cluster really close together, we call that compression. And when all those air molecules are colliding with each other in that region, more collisions means more impulse, right? You guys remember impulse, right? So impulse is change in pressure is force times change in time. So if we have a lot of impulse in this system, then there must be a lot of force as well, right? A lot of different forces changing the momentum of all of those gas molecules. And when we have a lot of force like that distributed over a certain region, a certain area, then we call that pressure, right? And so in this region here in the middle, so this region right here, the pressure is high. Okay? It may not be really high, it may just be high relative to the rest of the air molecules in that area. So the pressure is high here, but over here we can see that the air molecules are, in this region right here, the air molecules are spread apart. And in that region, there's going to be less collisions, less impulse, less force due to those collisions, and therefore lower pressure. And so in this region, the gas expands a little bit and the pressure is lower. So we have a region where the pressure is high and a region where the pressure is low. And you can see in between, there's a little bit of a gray area, right? So it's not black and white, there's a gray region. We can actually plot the pressure as a function of this x direction, let's say here. And that would look like the following. So maybe I'll zoom in one more, it's just a little bit easier to see. So if I put pressure on my y-axis and I put position here on my x-axis, then what I see is I'm at a region of high pressure here, and then low pressure here. By the way, this is gauge pressure. See, maybe I can make the pen stroke smaller and that's better. This is gauge pressure. So when I draw the pressure going negative here, it means it's lower than the atmospheric pressure. Let me actually try to make this. Let me try to make this plot so that it matches with what we see above. Now that I think about it, that might be a better way to do it. So the lowest pressure occurs there. Let's try that again. Lowest pressure, and then back up like this. High pressure, back down like this, and then back up. Not perfect there, but these peaks are meant to be at the same height. These troughs are meant to be at the same low here. And so this region corresponds here to this region. This region here corresponds to this region here. I didn't line them up perfectly, but there you go. And so there's an amplitude there, right? There's an amplitude. This thing can be written down as like a sine or a cosine. And we can describe the change in pressure using a wave-like expression. Okay. Now, sound waves are oftentimes referred to as pressure waves for this reason here. If I smack a drum like this, it makes a sound, and that sound is vibrations of air molecules moving through that medium, the air, and there's a corresponding pressure change, pressure wave that goes through the air, increasing and decreasing, and then increasing and then decreasing the pressure as that wave moves through. So sound waves are sometimes referred to as pressure waves. So sound waves are pressure waves. Okay, these two things are equal. Any questions up to this point here? Okay, so no questions here. So maybe now I'll ask a question to you guys. I won't type a question out or anything, just kind of a conceptual, like just think about it kind of question. So this is what the pressure wave looks like for a drum. So you smack a drum and the drum starts vibrating and, you know, emits a sound from the drum. What about if you were to, let's say, pluck a string on a stringed instrument like a guitar or a violin or something? Is the wave going to look different, or is it going to be the same? So that's the question. If you were to pluck a string on a guitar, would the wave here, the pressure wave, look any different? So yes, but unsure unsure of your answer. Okay. Okay, we got one person for the same, another person for yes, but unsure. So Kevin, maybe you're unsure about that as well. It'd be the same because it's still creating sound waves. Okay. Anybody else want to give an answer there? Anybody else have any input? Does it depend? Okay, so the answer to this question is that it is the same. It will be the same. In general, again, sound waves and pressure waves are the same. So any sound is going to create these pressure variations in the air. What might change, for example, like this drum here might have a certain characteristic frequency or fundamental frequency here of vibration. And you might pluck a string on a guitar, and the fundamental frequency for that string is different than the fundamental frequency for the actual drum. And so in that sense, the frequency of the wave might be different, but in principle, the wave will look the same, right? So in general, the sound waves are going to be pressure waves like this, and they'll just be small variations in pressure propagating through space or through air with the speed of sound. Okay. All right, so let me just quickly look at the chat there. Some people, okay. Well, that's good if you were thinking of frequency. So we will talk more about that pretty soon here. Let's talk about sound level, sometimes called sound intensity level, which is maybe a little bit of a point of confusion for students sometimes. Luckily, this book calls it sound level instead of sound intensity level. So we'll try to stick to that. So sound level. What is sound level? And my handwriting is bad all of a sudden, so let me rewrite that. Sound level. Sound level is a way of kind of classifying the volume of the sounds that you hear. So this is where the decibel scale comes from. Deci is a metric prefix meaning 1/10, right? Like centi is 1/100th, deci is 1/10. So decibel is 1/10 of a bell. We're not going to talk about bell ever, okay? Read about it in the book. There's a blurb about it, but we're never going to use bells, okay? Only decibels. So sound level, what is it? Well, it's a really arbitrary definition. So it's not something that's very intuitive at first, but what makes it intuitive is the size of the scale. There's this thing called the threshold of hearing, okay? There's this thing called the threshold of hearing. And what is this threshold of hearing? Well, it's the intensity of sound that you can just barely hear. So it's the minimum intensity. So the threshold of hearing, which we call I0 because it's the initial intensity that you can begin to hear at, is 1 times 10 to the minus 12 watts per square meter. Those are the units for intensity, right? It's power over area, so it's watts per meter squared. So 10 to the minus 12, that's quite a small number. Order of magnitude is 10 to the minus 12. Now, if we think about loud noises that we can hear, we could imagine asking the following question. How loud or how much intensity would a sound need to have for my ears to start bleeding or for me to be in pain, right? My ears are hurting. And in that case, the intensity for the threshold of pain, as it's called, threshold of pain, is actually surprisingly 1 watt per meter squared. So if your ear is experiencing an intensity of 1 watt per meter squared, That's quite a lot, simply because the eardrum of your ear is quite small, right? So if you have 1 watt per square meter, maybe you could go and calculate the amount of um, power that is being deposited on the size of your eardrum. And it may look like a small number at first, but then you could go and calculate the amplitude of vibration for that and see that the amplitude of vibration is quite large compared to the size of the eardrum. In which case, it's like the sound waves themselves are like pulling apart your ear, right? So that's why you would experience pain. And so here we have a range of values that is just so astronomically large, right? 10 to the 12 orders of magnitude. Excuse me, 10 to the 12 orders of magnitude. I mean, 12 orders of magnitude, right? A power of 10 is an order of magnitude. So we have 12 orders of magnitude. That's such a large range of intensities, right? So what we do is we take the logarithm of the intensity. By taking the logarithm of the intensity, we change the 12 orders of magnitude into something like 12, right? So a scale from 1 to 12. Well, a scale from 1 to 12 is maybe a little bit small. So instead of just taking the log, we take the log and then we multiply it by 10. And we multiply it by 10, now we have a scale that ranges from roughly 0 to 120. That's the idea behind sound level. So to create a human scale, or we could even say human-friendly scale, what we do is we define a quantity beta, the Greek letter beta, makes the same B sound, as 10 decibels, so 10 dB. These are units, right? Units times the log of the intensity of the sound that you're hearing divided by a constant, and that constant is the threshold of hearing. Okay? And this scale is very human because it ranges from 0 to 120, right? It's like the Fahrenheit temperature scale. It ranges from roughly like a little bit under freezing, a little bit below 32 degrees, all the way up to maybe as high as 120 degrees in the desert, right? So that's the idea. It's just it's strictly a mathematical definition. There's no physics here at all. This is just purely math. But in order to talk about certain applications and stuff, we kind of want to go in this route because it makes it a little bit easier to understand. Plus, I mean, what's your experience with with hardware, right? With speakers and things, maybe they have a certain decibel rating, right? Maybe you've heard your ear shouldn't be exposed to some number of decibels for a certain period of time, or it'll cause damage. There are laws that are written in terms of decibel level, right? So I think one example is like a car muffler can't be above a certain decibel level, or it's considered like a disturbance, to the public or whatever. So certain things like that. So the decibel scale is a real human-like scale here. So let's take a look at some examples of what we might encounter in our everyday lives here. So if you hear a whisper, passing secrets, right? We're in high school, we're whispering to each other, the teacher doesn't hear. We're looking at around 30 decibels. 30 decibels. If you're just talking in normal conversation, kind of like how I'm talking to you guys right now, about 65 decibels. Of course, that depends on the volume you have your speakers set to, but if you were maybe in the room with me right now and I was talking to you, it'd be about 65 decibels. Probably if we were in the classroom, I might even be talking a little bit louder because I'm trying to project my voice so people in the back can hear me, right? And so maybe we could even say, there's a range on this, maybe somewhere between 60 and 70 decibels for just normal talking. And of course, the value of the intensity changes based on how far away you are from the source. So if I'm whispering directly into your ear, passing a question that's going to be on the exam to you, but I don't want the other students to know, right? If I'm right up in your ear, it might be 30 decibels, but if I'm whispering across a room, that's going to be much lower, right? That's going to be maybe like 10 decibels. You're barely going to be able to hear me. Let's see, let's maybe do one more. Loud rock concert. So loud rock concert. Maybe that means you're somewhere in the middle or you're real close to the speakers. You're looking at 120 decibels. And this is right around the threshold of pain. This is about 1 watt per meter squared, or excuse me, this is exactly 1 watt per meter squared here. So this would be like the threshold of pain. Okay. Maybe let's give one example a little bit closer to the threshold of hearing. The book gives the rustling of leaves to be about 10 decibels, so really close to the limit at which you can hear. So maybe that means a light wind, right? There's a light breeze. You can't hear the wind, but you can hear the moving, the rustling of some leaves on the ground. Okay. So let's just go straight into like a practice problem here. And we'll talk about this idea of sound level and sound intensity. Okay, so let's go ahead and pull this example here. Let me go ahead and type this one because then we don't have to worry about zooming in, and it's not that long of a question here. And maybe actually I'll change the numbers on it a little bit. So at a busy street corner, the sound level is, let's change it a little bit, 72 decibels. What is the intensity of sound there? If you were to double the distance you are away from the street corner, how would that affect the decibel level? Okay, so I added a second part to the question too, which I think is maybe a little bit interesting here. There's no figure or anything for this kind of question, so I'll go ahead and read the question to you guys again, and then let you work on it for a couple minutes. So at a busy street corner, the sound level is 72 decibels. What is the intensity of sound there? If you were to double the distance you are away from the street corner, how would that affect the decibel level? So we're looking for intensity, and we're looking for let's say beta twice as far. So this one will take you maybe, I suspect this one might take you a little bit longer because this is a new concept, and solving, for intensity with a logarithm maybe is something you'll have to think back to your pre-calculus or algebra class, right? So let me know if there's a question, if you get stuck on that, so I can help you out. But I'll let you guys work on this one for maybe like 5 minutes or so, and then we can go over it. Oh, okay, I see your message. Okay, we see one person has some answers here. It looks like Denelise and Kevin have similar answer there for part A. Christine also, okay. That's good. So we have some agreement. Maybe that means we're doing it correctly. Evelyn, Liliana, okay. Give maybe another 2 minutes on this one, and then we'll go over the question. Again, if you're stuck, let me know. I can help you out so you can finish it before we go over it. So 2 more minutes. One more minute. Okay, another 15 seconds or so. I'm going to go over the question. Okay, so this question is quite the exercise in algebra review. I'm sure some of you have noticed. So the sound level beta is 10 times the log of the intensity divided by the threshold of hearing, I0. In order to go after the intensity here, we have to remember how to undo the logarithm. The first thing that we should do is divide both sides of the equation by 10. Let's go ahead and change the colors here so it's a little bit easier to follow each step. So divide both sides by 10. And then what we have is beta over 10 is log of I over I0. Now what we want to do is we want to cancel the logarithm somehow. The way to do that is to realize that if y equals the log of x, then that implies x is equal to 10 to the power y. So what we can do here is we can put these two terms in parentheses like this, and then exponentiate both sides. So we raise both sides of the equation up into the exponent. So 10 to the beta over 10 has to be equal to 10 to the log I over I0 if beta over 10 is equal to log I over I0, right? So then that allows us to, maybe we'll go to purple here, cancel the logarithm with the power of 10. Now over here, there's no cancellation, okay? Don't make the mistake of seeing a 10 here and a 10 here. Okay, cancel the 10s. That would be an algebraic mistake, okay? So we leave the left side as is. So we have 10 to the beta over 10 equals I over I0. And this tells us that the intensity I is equal to I0 times E to the beta over 10. Okay, so exponential relationship between the intensity is an exponential function of the sound level. The sound level is a logarithmic relationship with the intensity. Okay, so now we can plug everything into the right-hand side because what we're looking for is the left-hand side, right? So this is what we want to know right here. And we know this guy right here, the beta, is 72 decibels, right? And we know that the threshold of hearing, which is just some constant, 1 times 10 to the minus 12 watts per meter squared. Okay. And so when we plug all of this in, we have, basically 10 to the minus 12 times E. Oh my God, I made a big mistake, didn't I? Where's my mistake? How come nobody said anything? Look at this. I totally changed. I went from 10 to E. Let's fix that real quick. So that should be a 10. That should be a 10, not an E. So fix that in your notes if you were copying that down and you were confused. That should definitely be a 10 there. So I equals I0 times 10 to the beta over 10. Next time, if you guys see a mistake, let me know, okay? And then I can fix it. So plugging everything in, we're going to get approximately something around 10 to the minus 5, 10 to the minus 6. What did you guys end up? Okay, yeah, 1.58. I'll just grab one of your answers here. I'm pretty sure everybody got this one correct. Watts per meter squared there. Okay, so with that information, we're able to work on the second part of the question. So this is the answer for the first part here. This is the intensity of the sound at the busy street corner described in the problem statement here. Now the second question is right here. If you were to double the distance you are away from the street corner, how would that affect the decibel level? Well, you have to remember, so this is now the next part of the question. You have to remember that intensity let's write it this way, because this is what I mentioned earlier. So the intensity initially times the distance initially squared is equal to the intensity later, after we move further away, times the second distance squared. We're going to compare the intensities now. That's what we're being asked to do. Actually, that's not what we're being asked. That's what we have to do first in order to get the decibel level. So the intensity changes if we double the distance we are away, right? So if we double the distance we are away, then that means I can write I1 times R1 squared divided by R2 squared equals I2. I2 is what I want to get. This is the intensity after we get twice as far away. So this is intensity after doubling, excuse me, doubling the distance. Okay. And what is R1 divided by R2 if we're doubling the distance? Well, R1, let's say R1 is like 10 meters, right? Then that means R2 is 20 meters. So 10 over 20 is going to give us a factor of 1/2, right? So R1 over R2 is 1/2. But we're not after R1 over R2, we're after R1 squared over R2 squared. So what we can do is we can just square this number right here, right? So R1 squared over R2 squared is 1/4. So our intensity I2 after doubling the distance is equal to 1/4 times I1. Of course, we have I1 from the last part, so we can plug in and see that, what is it going to be? So 10 to the minus 6, so it's going to end up being 3, 9, something like 3.9 times 10 to the minus 6 watts per meter squared. You guys can check me on that. I just did that in my head real quick. So this right here is now the intensity that we would use. Probably just right here. In our formula now for beta. So beta is 10 log I over I0. Right? So if we now go and plug in this new intensity that we have, we're further away from the loud street corner, we can calculate a new sound level for being twice as far away. So 10 log 3.9 times 10 to the minus 6 watts per meter squared over 10 to the minus 12 watts per meter squared. You can put the 1 times 10 to the minus 12, but you really don't need the 1 to be there, right? You could save yourself some time on the calculator just writing 10 to the minus 12. And when you calculate this, what do we get here? I believe Kevin has the correct answer here, 66 decibels. It's certainly not 36 decibels. It's not going to decrease by a factor of 1/2. So the correct answer there, I believe, is 66 decibels. Let me quickly explain what happens when you change the intensity. Okay. Suppose we have a sound. Suppose we have a sound, beta 1, and it's 100 decibels. Okay. There's a corresponding intensity for this, and the intensity for 100 decibels is 1 times 10 to the, to the minus 2 watts per meter squared. In order to decrease the sound level by a factor of 10, so beta 2, if I want to increase the sound level by a factor of 10, in other words, down to 10 decibels, the intensity for a 10 decibel sound, I2, is 1 times 10 to the minus 10 watts per meter squared. Excuse me, times 10 to the 11, times 10 to the minus 11 watts per meter squared. You can check this for yourself. I'll leave this as something for you to check for yourself by plugging in those intensities into your calculator or doing it by hand. Since these are all powers of 10, you can do the logarithm really easily. Log of 100 is 2, log of 10 to the 5 is 5, right? So you can do these really easily yourselves. Notice that in order to decrease the decibel level by a factor of 10, the ratio of the intensities has to decrease by a factor of 10 as well. So in going from minus 2 to minus 11, that's 10 orders of magnitude. So check that for yourself. So what then happens if you, let's say, decrease the intensity by a factor of 2? Okay, let's take a look at that. So if the intensity 1, let's say, is, let's just pick maybe, let's say the intensity is 10 to the minus 6, kind of similar to what we had in the last problem. If the intensity is 10 to the minus 6 watts per meter squared, then the decibel level, again, you check this yourself. I'm just kind of doing this in my head here. This is going to be 60 decibels. Okay, 60 decibels. Now, if I cut the intensity down by only a factor of 2, which would change this to a 0.5, or let's actually, as a matter of fact, let's leave it as a fraction here. Let's put 1/2. So 1/2 times 10 to the minus 6 watts per meter squared. Matter of fact, let me just put I1 here. We'll do this analytically. Beta 2 is going to be equal to 10 times the log of I2 over I0. That's going to be equal to 10 times the log of 1/2 times I1 over I0. And by the properties of logarithms, I can break this logarithm into the following two logarithms. I have the product of two numbers in the logarithm, so I can break that into a summation of logarithms of each individual term. Okay, so this is the change in the decibel level, right? Because this is simply beta 1. 10 times the log of I1 over I0 is just our 60 decibels. So if I cut the intensity by a factor of 2, I cut it in half, I simply add log of 1/2 to the sound level. And log of 1/2 is a negative number, right? Because the log of a fraction, which is, the log of a number which is less than 1 is a negative number, right? So another way of recognizing that is you could break this log down one more time into the log of 1, which is 0, minus 10 times the log of 2, right? Whenever you have division, that is subtraction of logs. So this one goes to 0. So we can see that the decibel level, when you cut it in half, you simply subtract 10 times the log of 2. And 10 times the log of 2 is roughly 3. So minus 10 times the log of 2 is roughly 3. So you're going to subtract about 3 decibels, something like that. Let's go ahead and go over here to Wolfram Alpha and get an exact answer on that. So 10 times log of 2. Let's see if it uses base 10 here automatically. I'm not actually sure if it will or not. Yeah, it tried to use natural log first. Yep, about 3.01. About 3.01 is 10 times log of 2. So whenever you double or cut the intensity in half, so if you double the intensity or you cut the intensity in half, you can always add or subtract 3 decibels. Okay, so it tells you a little bit. It tells you a little bit about how sound level changes. For example, if you have 1 speaker versus 2 speakers. So if you add in a second speaker, you don't really increase the decibels by much. So assuming the sound, the power of the 2 speakers is the same. So let's say you have a 1 watt speaker and another 1 watt speaker, and you put them next to each other, at max power, then the decibel level at max power only increases by about 3 decibels. Okay, if you take one of the speakers away, it goes back down by 3 decibels. So every time you add 3 decibels, you double the intensity. If you cut the intensity in half, you subtract 3 decibels. Let's go ahead and take a look at go ahead and take a look at another example here. I believe I had another example ready to go. Where was that at? Oh yeah, here it is. Okay, again, I'll just type it. So we looked at what happens when you double the intensity, right? Or rather, cut the intensity in half. So if you were to double the intensity, you would add 3 decibels. You cut it in half, you subtract 3 decibels. Okay, what about, let's look at it like a situation where we have a bunch of trumpet players, okay? So a trumpeter plays at a sound level of 75 decibels. 3 equally loud trumpet players join in. Okay. What is the new sound level? Let's work in groups on this one. We haven't done any groups yet, so I'll put you guys into rooms. Can you tell me in the chat if you do not have a microphone? Tell me in the chat if you do not have a microphone. That way I can, there's no silent group. I can match at least one person with a microphone per group. So type in chat You can just take a picture of this, just use your phone or something, copy it into the notes later. Okay, so Sammy, Ju, and Christiana don't have microphones. Okay. I'll just manually create the rooms, and then I can spread the three of you out. There we go. And then I'll put this. All right, so go ahead and jump into your groups. Maybe about 5 minutes for this question. It shouldn't take much longer than that. And then if everybody's kind of getting it, we can kind of go through it quickly. If we're still struggling after 5 minutes, then I'll go through it a little bit slower. So all the rooms are open. Go ahead and join your rooms. Just take a picture on your phone and you can copy it into your notes later. Save a little bit of time. And those of you who happen to be watching the recording at home, just pause the video and work on the question. And I'm just going to pause the recording. And so it's just going to pick right up when everyone comes back in. Okay. Welcome back, everyone. Let's go ahead and go over the question now. Feel free to stop me if you have a question. I'm going to slow down a little bit. This example follows initially kind of like the last example we did. We're given a sound level, 75 decibels, and we need to first calculate the intensity of one trumpet. So that's kind of, let me write down the strategy here. So first we want to calculate I for one trumpet, right? And then what we want to do is we want to have the intensity of 4 trumpets, which is going to be 4 times 1 trumpet. This is not always the case. You can't always just multiply by a factor to get the new intensity. An example of when you can't do that is if the trumpet players are at different distances away from you. So if one trumpet player is like 2 meters away and the other trumpet player is like 3 meters away, well, the distance that the second trumpet player is away from you is like 1.5 times bigger than the distance of the first one. So that's going to change the intensity, right? It depends on distance squared. So they better all be in the same location if you're going to multiply the intensity by a factor like this. Otherwise, what you should do is add the intensities. So you'd have an intensity for trumpet player 1 plus an intensity for trumpet player 2 plus an intensity for trumpet player 3, all the way out to however many trumpet players you have. And each of those intensities might be different because they're at different distances. In this case, we're looking at a situation where all those trumpet players are like on a stage, maybe part of a band, and we're equally far away from all 4 of them. So we'll multiply the intensity of 1 trumpet by 4 to get the intensity for 4 trumpets. And then what we're going to do is we're going to take this information and calculate the new beta value for 4 trumpet players. Okay. Now, I will go through the complete solution here for this, but there is a nice trick that you can use stemming from, I think, maybe 1 or 2 examples ago, having to do with what happens when you double the intensity, right? We said if you double the intensity, you add 3 decibels. Well, if you quadruple the intensity, that's the same as doubling the intensity and then doubling the intensity again. So in that case, you'd add 6 decibels, right? So we can already kind of have an idea of what the answer should be. It should be 81 decibels without doing any calculations. And it's really nice to be able to kind of reason that out. So again, the logic on that is if the intensity is going to go up by a factor of 4, that's the same as doubling the intensity and then doubling the intensity again, right? The intensity times 2 again is times 4. So add 3 decibels every time you double the intensity. So add 6 decibels in this case. All right, so how do we calculate the intensity for one trumpet player? Well, it stems from the definition of sound level. If we solve for the intensity in the sound level equation, we end up with this equation here. I'm not going to go through this part again because we did that already. In order to cancel the logarithm, you have to exponentiate both sides to the power 10, right? And so forth. You end up with this expression here. And you want to just go straight to your calculator on this. So I have Wolfram alpha over here to calculate this for me. So 10 to the minus 12 times 10 to the beta over 10. And beta is 75 in this case. And 75 over 10 is 7.5. So 10 to the 7.5 times 10 to the minus 12. And we get, for our answer here, 31.6 times 10 to the minus 6. 31.6 times 10 to the minus 6 watts per meter squared. Just double check I got the order of magnitude there right. Wolfram alpha doesn't always write it in scientific notation, so yeah, so this looks correct here. Now that we have this, like I said, we can take this and plug it in to this expression to get the intensity for 4 trumpet players. So the intensity for 4 trumpet players is 126.4 times 10 to the minus 6 watts per meter squared. And I'm not paying much attention to significant figures here. We can round the answer to the end, or sorry, we can round the answer at the end to 2 sig figs, right? So we expect an answer of 81 decibels. So let's see what happens here. Now we can calculate beta. So beta is 10 times the log of I4 over I0. And again, we have all of this information here, so we simply need to plug it into a calculator. So just make sure that when you plug it in, you have your parentheses in the right spot. Well, I definitely made a mistake somewhere here. I think the intensity is fine. I think the mistake is here on my calculation somewhere. See if I can spot it here. Oh, oh no, that's fine. Oh, it's using natural log. That was why. Okay, there we go. Yeah, be careful about that. If you use Wolfram alpha, just be careful. If you type log, it uses the natural logarithm. So we get here for this answer 81.017, right? So decibels. So this is going to be 81 decibels here. Okay, which matched our prediction, right? So this was our prediction, 81 decibels. So doubling the intensity again adds 3 decibels. So if we double the intensity, that's 2 times. Then if we double it again, that's 4 times. So doubling it twice adds 6 decibels. It's a nice little trick to keep in your toolbox there. Any questions about that one? So go ahead, open it up to questions here if there are any. If not, we can go forward with some new material. You can give me a thumbs up or something. Okay, so let's go ahead and move to the next question here. I have a question that I kind of just prepped there while you guys were in the groups. I'm going to move it up a little bit so we save some space. So for this question, I have to remind you that formula we came up with from the last chapter's material. So I kind of wrote that beneath there. The idea here for this question is exactly what I was kind of talking about kind of towards the beginning of the class, which was that when you have these waves in sound, these pressure waves, these air molecules are vibrating back and forth. And I mentioned that if the amplitude of that vibration is large, then that means that the amplitude of vibration of your eardrum is going to be large compared to its size. And so that's what's going to cause you to experience pain, right? If your eardrum is being ripped apart by these vibrating air molecules, that's going to hurt. So that's the idea behind this question here. And while you guys are working on this question, I'll actually look up some information on the size of the eardrum. I don't know if it's in the book. I can check the book, but I was planning on just Googling it, kind of get the size of the area of the eardrum there. So we'll have a comparison to make between the amplitude of vibration here of these air molecules and the actual dimensions of the eardrum. So here's the question. Calculate the displacement of air molecules for a sound frequency of 400 hertz at the threshold of pain. Okay, 400 hertz at the threshold of pain. Threshold of pain, recall, so this is maybe something I also should have said. The threshold of pain is 1 watt per meter squared for the intensity. There's some other things that I need to give you here. I'll put you guys back in groups as well. We can do new groups. The other bit of information that I need to give you here is the speed of sound. We're talking about sound waves here, so this is going to be the speed of sound. We'll take it at room temperature, 343 meters per second. And we also need to know the density of air, right? Now, the density of air is about 1,000 times less than water. If you want to remember 1 kilogram per meter cubed, that's pretty good. We can do a little bit better though. We'll take the density of air to be 1.29 kilograms per meters cubed. So 1.29 kilogram per meter cubed. There's about a kilogram worth of air in your refrigerator. If you actually measure out the dimensions of your refrigerator, like refrigerator plus freezer, it's about 1 cubic meter. It's got about a kilogram and a third of air inside your refrigerator. Okay, so I'll give you guys again like maybe 5 minutes or something to work on this one. I'll put you in the breakout rooms here again, and let's mix up the groups a little bit. So maybe swap them a little bit like this. Ah, that's fine. Okay, I don't think I put any. Okay, in this group there's two people without a microphone. I think. So let's actually do this like that. Okay, I think that's pretty good. So the rooms are open. So go ahead, take 5 minutes to work on that. I'll come check on you guys while you're working. Go ahead and join your rooms. Just take a picture of the question, save yourself some time copying it down. Those of you who are watching on YouTube, again, in the blink of an eye, we'll be back to work on the solution, but you should pause the video and try the problem yourself, and then compare what you have with what we get when we're back. So I'll see you in a blink of an eye.